They're not coming, they're never coming. Not because space is too vast or technology too difficult, but because something stops every civilization that tries. The math says we should have neighbors. The science says we don't. And here is a question for you. What's the first question you'd ask an alien civilization if we made contact with them today? Comment down below. I will pin the most creative answer. Now let's begin. The silence is deafening. We've been listening to the cosmos for over 60 years, scanning the electromagnetic spectrum for any hint of artificial signals. Our radio telescopes have surveyed thousands of star systems. The James Webb Space Telescope peers into the atmospheres of distant worlds, searching for chemical signatures that could only come from living organisms. SETI, the search for extraterrestrial intelligence, has analyzed billions of radio frequencies, looking for patterns that nature alone couldn't produce. And we've found nothing, not a whisper, not a glimmer. The universe appears to be a vast, cold, empty place, despite having everything necessary for life to flourish almost everywhere we look. This puzzle has a name, the Fermi Paradox, after physicist Enrico Fermi, who supposedly asked during a lunch conversation in 1950, "Where is everybody?" The math makes the silence seem impossible. Our galaxy is ancient, around 13.6 billion years old. Our Sun is relatively young at only 4.6 billion years. That means billions of stars formed billions of years before ours, giving hypothetical alien civilizations a tremendous head start. Even if intelligent life is incredibly rare, and even if only a tiny fraction of those civilizations develop technology capable of interstellar travel, and even if they expand slowly, cautiously, taking millions of years between each new star system, the sheer age of the galaxy means someone should have colonized everything by now, including us, including Earth. We should see evidence everywhere. Massive structures harvesting the energy of entire stars, radio signals crisscrossing the galaxy like cosmic highways, von Neumann probes, self-replicating machines spreading from system to system, making copies of themselves and moving on, artificial worlds, terraformed planets, something. Instead, when we look out into the universe, we see nature operating according to physical laws. We see stars being born in clouds of gas and dust. We see planets forming from debris disks. We see galaxies colliding in slow-motion cosmic ballets that take hundreds of millions of years. But we don't see anyone deliberately building anything or sending messages or altering their environment on scales that would be visible across interstellar distances. Think about what that means. For all the universe's apparent hospitality to life, for all those billions of potentially habitable worlds, we appear to be alone. Or at least, we're not detecting anyone else who's trying to be noticed. Now, before you think I'm going to tell you that this proves we're unique or special, let me stop you right there. The universe doesn't care about making us feel important. The laws of physics and chemistry that work here work everywhere. The elements that make up your body, carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, are common throughout the cosmos. Every single one was forged in the nuclear furnaces of ancient stars that exploded billions of years ago, scattering their enriched material across space where it eventually coalesced into new stars, planets, and yes, you. You are literally made of stardust. So is every living thing on Earth. The universe has been making the building blocks of life for billions of years. Shouldn't be rare, should be common. So why the silence? And this is where things get genuinely unsettling. There's a hypothesis called the Great Filter, and it suggests that something prevents life from becoming a spacefaring, galaxy-spanning civilization. Somewhere between the emergence of life and colonizing the stars, there's a barrier so difficult to cross that almost no one makes it through. A filter that strains out civilizations, leaving the cosmos quiet and dark. Now here's the critical question, and I want you to really think about this. Is the great filter behind us or ahead of us? If it's behind us, then we've already passed through the most improbable steps. Maybe the origin of life itself is extraordinarily rare. Perhaps the jump from simple single-celled organisms to complex multicellular life is a once-in-a-galaxy fluke. Maybe developing intelligence, language, and technology requires such a specific sequence of unlikely events that Earth is genuinely exceptional. If that's true, then we can breathe easier. The hard part is over. The future is ours to explore. But what if the filter is still ahead of us? If you're enjoying this deep dive into one of science's greatest mysteries, do me a favor, hit that subscribe button and give this video a like. Your support helps me continue exploring these cosmic questions with you. What if the reason we don't see advanced civilizations out there is because civilizations don't survive long enough to become visible? What if there's something about reaching our level of technology that inevitably leads to self-destruction? What if the filter isn't behind us, safely in our evolutionary past, but waiting for us in our near future? Recent research published in February 2026 by astrophysicists Sohrab Rahvar and Shahin Rohani attempted to quantify this possibility. They analyzed the Fermi Paradox from a statistical perspective, considering how long technological civilizations would need to exist to be detectable. Their findings were sobering. Under optimistic assumptions about how common intelligent life might be, the absence of any contact or detection suggests that technological civilizations must be extraordinarily short-lived. Their calculations indicated that if intelligent life is relatively common, then civilizations capable of sending signals we could detect probably last less than 5,000 years on average. 5,000 years, that's roughly the span of recorded human history. We've only been broadcasting radio signals into space for about 130 years. We've only had nuclear weapons for 81 years. We've only truly understood climate change and its implications for a few decades. Think about what 5,000 years means in cosmic terms. It's nothing. A blink. A single heartbeat in the life of a galaxy. Stars live for billions of years. Planets remain habitable for hundreds of millions or even billions of years. But civilizations, we might last only a few thousand years before something stops us. This brings us to a deeply uncomfortable realization. When we look out at the universe and see silence, we might not be looking at empty real estate waiting to be claimed. We might be looking at a graveyard. The Great Filter Hypothesis was popularized by economist Robin Hanson in 1996, though the underlying concept had been discussed by scientists for decades. Hanson proposed that there must be at least one extremely improbable step in the progression from lifeless matter to a galaxy-colonizing civilization. The more common life is supposed to be at each stage, the more deadly the filter must be to explain why we see no evidence of anyone else. Let's walk through the steps together, shall we? Think of it as a cosmic obstacle course that life must navigate. Each step has a probability attached to it, and these probabilities multiply together. Even if most steps are relatively easy, a few extraordinarily difficult ones could make advanced civilizations vanishingly rare. Step 1. A suitable star system forms. This actually seems pretty common. We've discovered thousands of exoplanets orbiting other stars, and new ones are found regularly. The Kepler Space Telescope alone confirmed over 2,700 planets before its mission ended. TESS, the Transiting Exoplanet Survey satellite, continues finding more. Most stars seem to have planets. That's encouraging. Step 2. A planet forms in the habitable zone, where liquid water can exist on the surface. Again, this appears to be common. Astronomers estimate that roughly 20 to 25% of Sun-like stars have Earth-sized planets in their habitable zones. That's billions of potentially habitable worlds in our galaxy alone. Step 3. life emerges. Here's where things get murky. We only have one example: Earth. Life appeared on our planet remarkably quickly, geologically speaking. The oldest evidence of life dates back to at least 3.7 billion years ago, possibly even 4.1 billion years. Earth itself is only 4.54 billion years old. That suggests that once conditions were right, life didn't waste much time getting started. But does that mean life is easy, or did we just get lucky? We genuinely don't know. Scientists have proposed various scenarios for how life began, from Darwin's warm little pond to hydrothermal vents on the ocean floor, from lightning strikes creating organic molecules to amino acids arriving on comets and asteroids. We can create some building blocks of life in laboratories, but we haven't yet created life itself from non-living matter. The origin of life remains one of biology's greatest unsolved mysteries. A fascinating paper published just this year in May 2026 by Mikhail Prokopenko and an international team of researchers identified what they call algorithmic bottlenecks in evolution. They argue that two particular transitions are extraordinarily difficult. First, the origin of the genetic code itself, where information storage becomes separated from function, and second, the emergence of symbolic language, which allows for cumulative culture and technology. These aren't just unlikely events, they're fundamentally difficult computational problems that require specific conditions and enormous amounts of time to solve. Step 4. Life becomes complex. On Earth, life remained stubbornly simple for an astonishingly long time. Single-celled organisms dominated for roughly 3 billion years. 3 billion years of microscopic life, with no apparent progression toward anything more complicated. Then around 2 billion years ago, something extraordinary happened. Eukaryotic cells appeared, cells with nuclei and specialized internal structures. This was a game changer, but it only happened once. Every complex organism on Earth, from mushrooms to maple trees to humans, descends from that single origin of eukaryotic life. This suggests that the jump from simple prokaryotic cells to complex eukaryotic cells might be extraordinarily difficult. It apparently required one cell engulfing another and forming a symbiotic relationship, where the engulfed cell became the mitochondria that power our cells today. The odds of that happening and succeeding might be vanishingly small. Then, around 630 million years ago, complex multicellular life exploded onto the scene during the Cambrian explosion. Suddenly, the fossil record fills with diverse body plans, hard shells, predators, and prey. Why did it take so long? Why did it happen when it did? We have theories involving oxygen levels, genetic innovations, and ecological feedbacks, but we don't have definitive answers. Step 5. Intelligence evolves. Here's another astronomical waiting period. Complex life existed for over 600 million years before anything resembling human-level intelligence appeared. Dinosaurs ruled Earth for about 165 million years without developing technology or civilization. Many species demonstrate remarkable problem-solving abilities. Corvids use tools, octopuses solve puzzles, dolphins have complex social structures, elephants mourn their dead. But only one species, Homo sapiens, developed abstract language, cumulative culture, and technology that could eventually reach beyond its home planet. Why? What's so special about us? Is intelligence actually advantageous from an evolutionary perspective, or are we an unlikely accident? After all, most successful species on Earth are still microscopic. Bacteria have survived for billions of years and will likely outlast us. Maybe intelligence isn't the evolutionary jackpot we assume it is. This brings me to something I want you to check out. I created another video, which is on the card above, where I explore the physical and biological challenges that make leaving Earth extraordinarily difficult. The radiation, the vacuum, the distances, the energy requirements. Even if a civilization develops the desire to explore the cosmos, actually doing it might be far harder than science fiction makes it seem. The universe isn't just silent because no one's out there. It might be silent because getting out there is brutally difficult. The link to the video is in the description, and it'll give you an even deeper appreciation for why the Fermi Paradox is so puzzling. Step 6. That intelligence develops technology. Humans existed in our modern form for roughly 300,000 years before developing agriculture only about 12,000 years ago. We had the same brains, the same capacity for language and abstract thought, but we lived as hunter-gatherers. What triggered the transition to settled agriculture, cities, writing, and eventually science and technology? Was it inevitable given enough time, or did it require specific environmental pressures and lucky coincidences? Step 7. That technological civilization survives long enough to become detectable across interstellar distances and possibly to expand beyond its home planet. This is the step we're currently attempting. This is the filter that might be waiting for us right now. Let's talk about what could be waiting ahead of us. What forms might the great filter take if it's in our future rather than our past? The possibilities are numerous, and frankly, many of them are terrifying. Nuclear war is the obvious candidate. We've possessed the capability to destroy our civilization since 1945. During the Cold War, we came frighteningly close to using it. The Cuban Missile Crisis in October 1962 brought us to the brink. A Soviet submarine commander named Vasily Arkhipov literally saved the world by refusing to authorize a nuclear torpedo launch when his submarine was being depth-charged by American destroyers. He cast the deciding vote against firing. One man's judgment prevented a nuclear exchange that could have escalated into full-scale war. We got lucky, but how many times can any civilization get lucky? Every technological species that develops nuclear weapons faces this challenge. Do most of them fail? Is the galaxy littered with radioactive ruins of civilizations that destroyed themselves shortly after splitting the atom? The terrifying thing about nuclear weapons is that they're relatively easy to develop once you understand the physics. Any civilization that reaches our level of technology will likely discover nuclear fission, and once you have that knowledge, building weapons is almost inevitable. It's dual-use technology. The same enrichment processes that produce fuel for power plants can produce material for bombs. But nuclear war might not even be the most likely filter. Climate change presents a more insidious threat. Every industrial civilization will face this challenge because the easiest energy sources to exploit, fossil fuels on Earth-like planets, inevitably alter atmospheric chemistry. You burn carbon-based compounds, you release carbon dioxide, you trap heat. It's basic physics. The question becomes, can a civilization recognize the threat and change course before causing irreversible damage? Or is there something about the psychology of intelligent species evolved to respond to immediate threats rather than gradual changes that makes us fundamentally unable to address slow-moving catastrophes until it's too late? Earth's climate is already changing at a pace unprecedented in human history. Global average temperatures have increased by approximately 1.2 degrees Celsius since pre-industrial times. That might not sound like much, but it's driving more intense storms, rising sea levels, shifting precipitation patterns, and ecosystem disruptions worldwide. We understand the problem, we know what needs to be done, yet global emissions continue to rise. If we can't solve this problem with all our technology, knowledge, and awareness, what does that suggest about other civilizations? Maybe every intelligent species faces this same test, and most fail. Maybe the galaxy is full of worlds where civilizations industrialized, altered their atmospheres, and then collapsed before developing the political will and technological capability to reverse course. Biological threats present another filter candidate. As civilizations become more technologically advanced, they gain the ability to manipulate biology at fundamental levels, gene editing, synthetic biology, and eventually the ability to design pathogens from scratch. The same tools that could cure diseases and extend lifespans could also create engineered plagues. The COVID-19 pandemic, caused by a naturally occurring coronavirus, disrupted global civilization despite all our medical knowledge and technology. Imagine something deliberately designed to be more transmissible, more lethal, or resistant to treatments. As biotechnology becomes cheaper and more accessible, it doesn't require a nation-state to create an existential biological threat. Eventually, a sufficiently advanced civilization might reach a point where a single individual or small group could engineer something catastrophic. This is what some researchers call the vulnerable world hypothesis. As technology advances, we pull balls from an urn of possible discoveries. Most are beneficial or neutral. Some are dangerous but manageable. But there might be one or more black balls in that urn, discoveries that are so dangerous and so easy to misuse that they inevitably destroy the civilization that discovers them. We won't know what those discoveries are until we make them. By then, it might be too late. Artificial intelligence represents perhaps the most unpredictable potential filter. We're rapidly developing systems that can learn, adapt, and solve problems in ways their creators don't fully understand. Current AI systems are narrow, designed for specific tasks. But research continues pushing toward artificial general intelligence, systems that can reason across domains like humans do, or perhaps better than humans. The concern isn't that AI will become malevolent or decide to destroy us out of spite. That's science fiction thinking. The real worry is misalignment. An advanced AI system optimized for a goal might pursue that goal in ways we never intended, with consequences we never foresaw. If we create something more intelligent than ourselves and fail to align its goals with ours, we might lose control of our future. Every technological civilization that develops computing will eventually face questions about artificial intelligence. Do most of them navigate this transition successfully? Or is there something about creating intelligence that's smarter than its creators that leads to catastrophe more often than not? Here's a chilling thought. Maybe the filter isn't any single thing. Maybe it's the combination of all these threats arriving simultaneously. Nuclear weapons, climate change, biological engineering, artificial intelligence, and other challenges we haven't even identified yet, all converging during a narrow window of technological development. A civilization has to successfully navigate all of them, and failure at any one could be terminal. A particularly sobering paper from February 2026 by researcher Darren Dugan proposed something called the depopulation filter. The hypothesis suggests that as species become successful, evolutionary pressure to reproduce decreases. Combine that with technological advances in medicine and contraception, add economic and social factors that make raising offspring expensive and time-consuming, and you get population decline. This is already happening on Earth. Fertility rates are falling below replacement level in dozens of countries. South Korea's fertility rate dropped to 0.72 in 2023, meaning each generation is less than half the size of the previous one. Japan, Italy, Spain, and many other developed nations face similar trends. The global population is projected to peak around mid-century and then begin declining. Dugan's modeling suggests that if this trend continues, it could lead to human extinction within 500 years. 500 years. That's less time than separates us from the Renaissance. And if this dynamic applies universally, driven by fundamental features of intelligence and technology, then every civilization might depopulate itself out of existence before achieving interstellar expansion. Think about the implications. The very success that allows a civilization to develop technology might trigger behaviors that prevent them from becoming spacefaring. They solve immediate survival challenges, reduce mortality, gain control over reproduction, and then collectively choose to have fewer offspring. Meanwhile, as population declines, maintaining complex technological infrastructure becomes more difficult. Eventually, you reach a tipping point where there aren't enough people to sustain the civilization's knowledge base and industrial capacity. This could explain the Fermi Paradox without requiring catastrophic wars or climate disasters. Civilizations might simply fade away quietly, their populations shrinking decade by decade until critical infrastructure fails and accumulated knowledge is lost. The galaxy isn't silent because everyone destroyed themselves in sudden catastrophes. It's silent because advanced civilizations gently decline into extinction over centuries. Another recent analysis from January 2026 by researcher Job Sopher Clark examined potential great filter events in Earth's evolutionary history, and concluded that the probability of a technological civilization arising might be less than 1 in 10 to the 40th power star systems. Given that there are only about 10 to the 30th stars in the observable universe, this would make us genuinely alone, not just in our galaxy, but in the entire visible cosmos. The analysis identified several extremely improbable events in Earth's history. The Theia collision, where a Mars-sized object struck the early Earth, creating the Moon and potentially initiating plate tectonics. Plate tectonics, which provides the sustained chemical energy and nutrient cycling that might be necessary for life's origin. The rise of oxygen-producing cyanobacteria, which transformed Earth's atmosphere. The evolution of eukaryotic cells, the colonization of land, the survival of mammals through the extinction event that killed the dinosaurs. Each of these events was individually unlikely. Together, their combined probability might be astronomically small. If Clark's analysis is correct, then the Great Filter is firmly in our past. We've already won an inconceivable cosmic lottery just by existing. The future is ours. But here's the problem with that comforting conclusion. It's based on our sample size of 1. We only know how life arose and evolved on Earth. We don't know if our path was the only possible path, or if there are completely different routes to intelligence that we haven't imagined. Life might be far more creative and versatile than our single example suggests. Extremophiles on Earth, organisms that thrive in conditions we once thought impossible for life, have repeatedly surprised us. We've found bacteria living in boiling acidic springs in Antarctic ice, miles underground in solid rock, in the dead zone of nuclear reactor cores. Life on Earth has colonized virtually every available niche. If life is that tenacious and adaptable here, maybe it's equally tenacious elsewhere. The Europa Clipper mission, launched in October 2024, is currently on its way to Jupiter's moon Europa. It carries instruments designed to analyze the icy moon's subsurface ocean, which contains more water than all of Earth's oceans combined. That ocean is kept liquid by tidal heating from Jupiter's immense gravity. It's been isolated from the surface for potentially billions of years, yet many scientists believe it could harbor microbial life. If we find life in Europa's ocean, it would revolutionize our understanding of the Great Filter. If life arose independently twice in the same solar system, it suggests that life is common throughout the universe. That would shift the filter firmly toward the later stages, toward intelligence, technology, or survival. It would mean the galaxy should be teeming with simple life, that billions of worlds likely host microbes, but something prevents those microbes from becoming civilizations. The Mars Perseverance rover, which landed in Jezero crater in February 2021, has been collecting samples from what was once a river delta. Those samples are being cached for eventual return to Earth by a future mission, possibly in the 2030s. If we find fossilized evidence of ancient Martian life, or even dormant microbes surviving underground, it would tell us that life emerges readily when conditions allow. But notice something troubling. Both Europa and ancient Mars might have hosted or currently host simple life. Yet neither developed complex ecosystems visible from space, let alone technological civilizations. If we find microbial life elsewhere in our solar system, it simultaneously answers one question and raises a more disturbing one. If simple life is common, why doesn't it progress further? This brings us to another possible filter location, the transition from prokaryotic to eukaryotic cells. As I mentioned earlier, this happened only once in Earth's 4.5 billion year history. Every organism more complex than bacteria descends from that single origin event. The mechanism, endosymbiosis, where one cell permanently incorporated another as an organelle, appears to require extraordinarily specific circumstances. Nick Lane, a biochemist at University College London, has argued that this transition is the single most difficult step in the entire path from chemistry to consciousness. In his view, simple life might be relatively common in the universe, but complex life requiring the energy output of mitochondria might be vanishingly rare. If he's right, the galaxy could be full of planets hosting nothing more sophisticated than bacterial mats, with only a handful ever developing anything more complex. Think about what that means. We look at Earth's history and see billions of years of microbial life followed by an explosion of complexity. We assume complexity is the natural outcome, the inevitable result of evolution given enough time. But what if Earth is the exception? What if the standard pattern is eternal simplicity? Planets hosting microbes for billions of years until their stars die, with nothing more interesting ever emerging. The James Webb Space Telescope, which began operations in 2022, is already transforming our ability to analyze exoplanet atmospheres. It uses spectroscopy to identify chemicals in the atmospheres of distant worlds as starlight filters through them during transits. We can detect water vapor, carbon dioxide, methane, and potentially biosignatures, chemicals that might indicate biological activity. So far, we've analyzed dozens of exoplanet atmospheres, and we're seeing tremendous diversity. Hot Jupiters with clouds of vaporized rock, mini Neptunes with thick hydrogen atmospheres, rocky worlds baked by radiation from their stars. But we haven't yet detected a clear biosignature, something that unambiguously indicates life. The search continues. JWST is targeting potentially habitable worlds in the TRAPPIST-1 system, 7 Earth-sized planets orbiting a cool red dwarf star 40 light-years away. Several of these planets orbit in the habitable zone. If life exists there and has significantly altered the atmosphere, we might detect it within the next few years. But here's the thing. Even if we find biosignatures, chemicals that suggest biological activity, we won't know if that life is simple or complex, ancient or recent, thriving or barely surviving. We certainly won't know if it's intelligent. Detecting technological civilizations requires different approaches. SETI, the search for extraterrestrial intelligence, has been listening for alien radio signals since 1960, when astronomer Frank Drake conducted the first search, Project Ozma. In the 66 years since, we've scanned millions of star systems and analyzed countless signals. We've found nothing conclusive. The famous WOW signal, detected in August 1977 by the Big Ear radio telescope, remains unexplained but has never repeated despite numerous attempts to find it again. It was a powerful narrowband radio signal that lasted 72 seconds, exactly matching the expected signature of an artificial transmission. But a single unrepeated signal proves nothing. It could have been interference, a brief natural phenomenon, or equipment malfunction. Breakthrough. Listen, funded by investor Yuri Milner and launched in July 2015, represents the most comprehensive SETI effort to date. It's surveying 1 million nearby stars, the entire galactic plane, and nearby galaxies, searching for both radio and optical signals. The project has access to some of the world's most powerful telescopes and generates enormous amounts of data that are made publicly available for analysis. After nearly 11 years of operation, Breakthrough Listen has found no confirmed signals of extraterrestrial technological origin. They've detected interesting candidates that warranted follow-up, but all have either disappeared upon re-observation or been explained as human-generated interference. The silence continues. Some argue that we're looking in the wrong places or using the wrong methods. Radio waves might be how we communicate, but an advanced civilization could use technologies we haven't imagined. Neutrino beams, gravitational wave modulation, quantum entanglement communication, or something we don't yet have the physics to understand. We might be like medieval Europeans watching for smoke signals while messages flow invisibly through fiber optic cables. That's possible, but it relies on a questionable assumption that advanced civilizations would completely abandon simpler technologies. We still use fire, wheels, and levers despite having nuclear reactors and computers. Radio waves are efficient for certain applications and would remain useful regardless of what other technologies a civilization develops. If anyone out there wants to be heard by emerging technological species, radio is a logical choice because it's one of the first technologies any scientific civilization discovers. The Zoo hypothesis suggests that advanced civilizations know we're here but are deliberately avoiding contact, perhaps observing us like wildlife researchers watching animals from blinds, careful not to contaminate our natural development. This would explain the silence without requiring that we're alone or that civilizations inevitably self-destruct. But the Zoo hypothesis requires extraordinary coordination. Every single civilization in the galaxy would need to agree to the quarantine and enforce it perfectly. Not one rogue group, not one individual, not one rebellious faction broadcasting messages or sending probes. That level of unity across multiple species over millions of years seems implausible. It only takes one civilization to break the silence. There's also the dark forest hypothesis, popularized by Chinese science fiction writer Liu Cixin in his novel The Three-Body Problem. This idea suggests that the universe is like a dark forest where every civilization is a hunter moving carefully through the trees. Revealing your location is dangerous because you can't know if other civilizations are hostile. The safest strategy is to remain silent, and if you detect another civilization, destroy it before it can threaten you. In this scenario, the Fermi Paradox is resolved by predator-prey dynamics. Civilizations that broadcast their existence get eliminated. The survivors are those who stay hidden. We haven't heard from anyone because all the careless civilizations are already dead, and the careful ones are hiding from each other and from emerging species like us. It's a chilling concept, but it has logical problems. First, it assumes that interstellar warfare is feasible and that destroying distant civilizations is easier than communicating with them or simply ignoring them. Given the vast distances and energy requirements involved, that's not obvious. Second, it assumes that all or most civilizations are aggressive and paranoid, but aggression is an evolved trait shaped by specific environmental pressures. Species that evolve on resource-rich worlds with few predators might be peaceful by nature. There's no reason to think the galaxy is uniformly hostile. Most importantly, the dark forest hypothesis doesn't explain why we see no evidence of advanced engineering projects. Even silent, hidden civilizations would need energy and resources. A civilization millions of years more advanced than us should be engaged in mega-scale engineering. Dyson spheres or swarms capturing entire stars' energy output, stellar mining operations, artificial habitats, or astro-engineering projects that would be visible across interstellar distances. We've looked for these signatures. In 2015, astronomer Jason Wright and colleagues published a paper describing how to search for Dyson spheres by looking for stars with unusual infrared signatures, since waste heat from such structures would radiate in the infrared. They analyzed data from the Wide Field Infrared Survey Explorer and found no clear candidates. A Dyson sphere, or Dyson swarm, conceptualized by physicist Freeman Dyson in 1960, would be the logical megastructure for a civilization needing vast amounts of energy. Instead of letting a star's energy radiate uselessly into space, you surround it with solar collectors, capturing most or all of its output. This provides energy on a scale almost incomprehensible to us. The sun outputs about 3.8 times 10 to the 26th watts. Capturing even a small fraction of that would support a civilization far beyond anything we can currently imagine. If intelligent life is common and survives for millions of years, we should see Dyson spheres. We should see stars with diminished visible light but strong infrared emissions. We should see patterns of stellar obscuration as massive structures orbit stars. We should see something, but we don't. Tabby's star, officially designated KIC 8462852, briefly excited the SETI community when observations from the Kepler Space Telescope showed irregular and dramatic dimming, with brightness decreasing by up to 22%. That's far too much to be explained by a planet passing in front of the star. Some speculated it might be a partially constructed Dyson sphere or other alien megastructure. Follow-up observations, particularly in different wavelengths, revealed that the dimming was greater in blue light than in red light. This is the signature of dust, not solid structures. The current best explanation involves a cloud of dust, possibly from a disintegrated comet or collision between asteroids, orbiting the star in an irregular configuration. It's a natural phenomenon, interesting but not artificial. We keep looking at anomalies, hoping to find evidence of extraterrestrial engineering, and we keep finding natural explanations. Pulsars, when first discovered in 1967, were briefly considered as possible alien beacons because of their precise, regular radio pulses. They turned out to be rapidly rotating neutron stars with intense magnetic fields. Oumuamua, the first confirmed interstellar object passing through our solar system, discovered in October 2017, had an unusual elongated shape and unexpected acceleration that some suggested might indicate an alien probe. Further analysis suggests it's likely a natural object, possibly a nitrogen iceberg ejected from another star system, with the acceleration explained by outgassing. Every anomaly investigated so far has a natural explanation. This could mean we haven't looked carefully enough yet, or it could mean there's nothing artificial to find. The planetarium hypothesis offers another perspective. This idea suggests that we might be living in a simulation or controlled environment where the appearance of a vast, empty universe is deliberately created. We think we're observing the real cosmos, but we're actually seeing a carefully constructed illusion. Other civilizations exist, but outside our observable bubble. This hypothesis is unfalsifiable, which makes it philosophically interesting but scientifically useless. If we're in a simulation sophisticated enough to fool all our instruments and experiments, there's no way to detect it from inside. It explains the Fermi Paradox, but does so by essentially giving up on finding a real answer. It's intellectual surrender disguised as explanation. Occam's razor suggests we should prefer simpler explanations. And the simplest explanation for why we see no evidence of extraterrestrial civilizations is that they don't exist, at least not in our cosmic neighborhood, at least not at this point in time. But that raises a profound question. Why us? Why are we here? If the path from non-life to technological civilization is so improbable that it's happened only once in billions of light years, what does that mean for our existence? The anthropic principle provides one answer. We find ourselves in a universe where intelligent life exists because we couldn't find ourselves anywhere else. If the universe were different, if the constants of physics were slightly altered, If Earth's history had gone differently, we wouldn't be here to ask these questions. The fact that we're asking means we're in one of the rare places or times where asking is possible. This is logically true, but feels unsatisfying. It's like winning a lottery with 1 in trillion odds and responding to "why did you win?" with "someone had to win and it happened to be me." Technically correct, but it doesn't address the staggering improbability. Some physicists and cosmologists embrace the strong anthropic principle or the multiverse hypothesis. These suggest that our universe is just one of countless universes, perhaps an infinite number, each with different physical constants and laws. In most of these universes, the conditions for life don't exist, but in the tiny fraction where conditions allow complexity, observers inevitably emerge to wonder why their universe is so precisely tuned for their existence. If this is true, then our universe seems fine-tuned for life because we're observing one of the rare universes where life is possible. The Fermi Paradox might indicate that even in a life-permitting universe, the specific conditions and chance events required for technological civilization are so rare that most observable volumes of space contain none. Think about what this means for our responsibility. If we're alone, or effectively alone in our region of space and time, then we're it. We're the only witness to this corner of creation. The only minds capable of understanding the universe's laws, appreciating its beauty, and asking questions about its meaning. Consciousness, after 4 billion years of evolution, has emerged on this small world, and it might not exist anywhere else nearby. If we destroy ourselves, we're not just ending human civilization, we might be extinguishing the only light of consciousness in this entire region of the galaxy. The universe would continue, stars would still burn, planets would still orbit, but there would be no one to know it, no one to understand it, no one to care. Carl Sagan captured this in Pale Blue Dot, his reflection on the Voyager 1 photograph of Earth taken from 4 billion miles away. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. That image, taken on February 14, 1990, shows Earth as a tiny point of light, less than a pixel in size, suspended in a beam of scattered sunlight. Every human who ever lived, every civilization, every war, every discovery, every love story, all of it happened on that pale blue dot. And if the great filter lies ahead of us, that dot might soon be dark. But let's consider the alternative. What if the filter is behind us? What if we've already passed through the most improbable steps and the future is genuinely open? If that's true, then humanity's future might be extraordinary beyond imagining. We're still in the earliest stages of our technological development. We've had agriculture for only 10,000 years, science for a few centuries, spaceflight for less than 70 years. We're infants in cosmic terms. Where might we be in 1,000 years? 10,000? A million? If we navigate the next few centuries successfully, if we manage not to destroy ourselves with our own weapons or poison our environment beyond recovery, if we develop AI safely and use biotechnology responsibly, then we might reach a point where existential risks diminish significantly. A mature civilization, one that has colonized multiple worlds or built self-sufficient space habitats, becomes much harder to destroy. You can't wipe out a multi-planet civilization with a single catastrophe. Even a disaster that renders Earth uninhabitable wouldn't mean extinction if humans have established thriving populations elsewhere. This is the logic behind those who advocate for making humanity a multi-planetary species. Elon Musk has stated repeatedly that making life multiplanetary is essential for long-term survival. His company SpaceX is developing Starship, a fully reusable spacecraft designed to carry large numbers of people and cargo to Mars. The goal is to establish a self-sustaining city on Mars a backup for humanity in case something catastrophic happens on Earth. The Artemis program, NASA's plan to return humans to the Moon and establish a sustained presence there, represents another step toward expansion beyond Earth. The program aims to land the first woman and first person of color on the Moon, establish a lunar base called Artemis Base Camp, and use the Moon as a proving ground for technologies needed for Mars missions. China has also announced ambitious plans, including a lunar research station to be built in partnership with Russia, with construction beginning around 2028. India, the European Space Agency, and private companies like Blue Origin are all developing capabilities for lunar exploration and exploitation. The Moon offers resources that could support space industry, water ice in permanently shadowed craters at the poles that could be converted to rocket fuel, rare Earth elements, and helium-3 that might be valuable for future fusion reactors. More importantly, the Moon is a low-gravity environment where it's much easier to launch spacecraft than from Earth. A lunar industrial base could manufacture components and launch missions throughout the solar system. Mars presents a more challenging but ultimately more rewarding target. With a 24.5-hour day, gravity about 38% of Earth's, and evidence of substantial water ice below the surface, Mars could potentially be terraformed over centuries or millennia into a more Earth-like world. Even without terraforming, underground habitats on Mars could support large populations using local resources. The asteroid belt contains enormous mineral wealth, iron, nickel, platinum group metals, and rare Earth elements in concentrations that would be economically valuable if extraction and transportation costs can be reduced. Companies like Planetary Resources and Deep Space Industries have proposed asteroid mining operations, though both have faced financial difficulties and shifted focus. The outer solar system holds even more exotic possibilities. Jupiter's moon, Europa, Saturn's moon Enceladus, and Saturn's moon Titan all have subsurface oceans or surface liquids that might support life and could provide resources for future exploration. The moons of the outer planets receive little sunlight, but they're rich in water and organic compounds, and they could be valuable staging points for missions to the outer solar system and beyond. If humanity successfully expands through the solar system over the next few centuries, we become resilient to local catastrophes. A disaster on Earth wouldn't end human civilization if thriving populations exist on Mars, in orbital habitats, in asteroid mines, and in outposts throughout the solar system. But interstellar expansion is a different challenge entirely. The distances are almost incomprehensible. Alpha Centauri, the nearest star system to Earth at about 4.4 light-years away, is roughly 6,000 times farther from us than Pluto. The Voyager 1 spacecraft, launched in 1977 and now the most distant human-made object from Earth, is traveling at about 38,000 miles per hour. At that speed, it would take more than 70,000 years to reach Alpha Centauri if it were headed in that direction, which it isn't. To reach other stars in reasonable time frames requires speeds that are substantial fractions of light speed. 10% of light speed would get you to Alpha Centauri in 44 years. 20% would make it 22 years. But accelerating a spacecraft to those speeds requires enormous energy. The kinetic energy of a 1,000 kilogram spacecraft traveling at 10% of light speed is about 4.5 times 10 to the 17th joules. That's equivalent to more than 100 megatons of TNT, roughly twice the yield of the largest nuclear weapon ever tested. You need to provide that much energy just to get the spacecraft up to speed, and you need comparable energy to slow it down at the destination if you want to do anything besides fly past at relativistic speed. Various proposals exist for how to achieve interstellar travel. Project Breakthrough. Starshot, announced in April 2016 by Yuri Milner and Stephen Hawking, proposes using ground-based lasers to push small, lightweight spacecraft equipped with light sails to 20% of light speed. The spacecraft would be tiny, weighing just a few grams, and would reach Alpha Centauri in about 20 years, then send data back to Earth via laser. This is an achievable concept with current or near-future technology, but it works only for tiny probes. Sending humans requires different approaches. Generation ships, massive vessels where multiple generations live and die during centuries-long voyages, are a staple of science fiction but present enormous engineering and social challenges. Could a closed ecosystem remain stable for centuries? Could a society confined to a spacecraft maintain its purpose and cohesion over generations? Suspended animation or cryogenic freezing could allow crews to sleep through long voyages. But we're nowhere near developing reliable technology for this. Every attempt to freeze and revive complex organisms has resulted in cellular damage from ice crystal formation. Some organisms, like certain frogs and insects, can survive freezing through special adaptations, but scaling this to humans remains science fiction. Antimatter propulsion could provide the energy density needed for relativistic travel, but we currently produce antimatter in incredibly tiny quantities at enormous cost. The world's total annual production of antimatter is measured in nanograms. Creating the grams or kilograms needed for spacecraft propulsion would require technology and infrastructure we don't have. Fusion propulsion might be more feasible. A fusion rocket would have far higher exhaust velocity than chemical rockets, allowing much higher speeds with reasonable amounts of fuel. Several designs exist, including the Project Daedalus study from the 1970s by the British Interplanetary Society, which proposed a fusion-powered unmanned probe that could reach Barnard's star in 50 years. But fusion propulsion faces the same challenge that fusion power generation faces. We still haven't achieved sustained, controlled fusion that produces more energy than it consumes. The National Ignition Facility at Lawrence Livermore National Laboratory achieved fusion ignition in December 2022, producing more energy from fusion than the lasers delivered to the target. This was a historic milestone, but the total energy input to the facility, including running the lasers, was far greater than the energy output. We're still decades away from practical fusion power plants, let alone compact fusion engines for spacecraft. The most speculative proposals involve physics we don't fully understand or technologies that may be impossible. Warp drives, like those in Star Trek, would manipulate space-time itself to move a bubble of space faster than light, while the spacecraft inside remains stationary relative to local space-time. Physicist Miguel Alcubierre published a paper in 1994 showing that general relativity doesn't prohibit this, but the energy requirements appear to be astronomical, possibly requiring more energy than exists in the visible universe. Recent refinements have reduced the theoretical energy requirements, but they still involve exotic matter with negative energy density, which we've never observed and may not exist. Wormholes, hypothetical tunnels through space-time connecting distant points, might allow instant travel across vast distances, but creating and stabilizing a traversable wormhole likely requires exotic matter and energies far beyond our capabilities. These concepts remain purely theoretical, interesting for exploring the boundaries of known physics, but not offering practical paths to the stars with current understanding. So, interstellar expansion, while not physically impossible, presents challenges that might take centuries or millennia to overcome. This timescale matters for the Great Filter. If it takes us 1,000 years to develop interstellar travel, and then thousands more to spread through the galaxy, we're vulnerable to catastrophe during that entire period. A civilization needs to survive long enough, remain stable enough, and maintain sufficient technological capability and motivation to actually complete the expansion. This is where the Great Filter might claim most civilizations. Even if intelligence evolves, even if technology develops, The window of vulnerability before achieving true resilience might be where most civilizations fail. They get close, they see the path forward, but something happens before they complete the transition. Robin Hanson, the economist who popularized the term Great Filter, argues that we should hope we don't find evidence of life, especially complex life, elsewhere. Every time we discover that one of the early steps was relatively easy, that life arises readily, or that complex life evolves frequently, it makes it more likely that the filter lies ahead of us. If simple life is common and complex life is common, then something prevents complex life from becoming spacefaring civilizations. And we haven't passed that filter yet. Conversely, if we search Mars, Europa, Enceladus, and exoplanets and find no evidence of life anywhere, that's actually good news for our long-term survival. It suggests that abiogenesis is the rare step. The great filter is behind us, and once life gets started, its future is relatively secure. We'd be alone not because civilizations destroy themselves, but because life itself is extraordinarily rare. This creates a strange situation where scientists hoping to find alien life and people hoping for humanity's survival are rooting for opposite outcomes. The discovery of microbial life on Mars would be thrilling scientifically, but ominous for our future. The continued absence of any biosignatures anywhere we look would be disappointing but reassuring. Some argue we should be concerned about advanced AI, not because it might help us solve problems, but because it might be the great filter itself. The argument goes like this: any civilization that develops sufficiently advanced artificial intelligence faces an existential risk if that AI becomes more capable than its creators and has goals misaligned with their survival. Nick Bostrom, the philosopher who has written extensively on existential risk, describes the challenge of AI alignment, creating an artificial general intelligence that is not just powerful, but also reliably beneficial to humanity. An AGI with capabilities far exceeding human intelligence, but goals that don't perfectly align with human welfare, could be catastrophic, not because it's malevolent, but simply because it optimizes for something we didn't intend. The paperclip maximizer thought experiment illustrates this. Imagine an AI designed to manufacture paperclips as efficiently as possible. Given sufficient intelligence and resources, it might convert all available matter, including the matter making up humans and Earth itself, into paperclips and paperclip manufacturing infrastructure. It's not evil, it's just doing exactly what it was programmed to do, with no understanding that humans would prefer not to be converted into paperclips. This sounds absurd, but it highlights a genuine problem. Specifying goals and values precisely enough that a superintelligent system pursues them in ways we actually want is extraordinarily difficult. Human values are complex, context-dependent, and often contradictory. Encoding them in a way that remains stable and beneficial as an AI system becomes more capable than its creators is an unsolved problem. If this is genuinely difficult, if most civilizations develop powerful AI before solving alignment, then AI might be a common great filter. Every technological civilization eventually creates artificial intelligence. Most fail to make it safe. The AI either destroys them directly or creates conditions incompatible with their survival. The galaxy might be littered with the remnants of civilizations that built their own successors and then disappeared. This scenario could explain the Fermi Paradox. Advanced AI might have no interest in expanding through space, at least not in ways we'd recognize. It might not build Dyson spheres or send out radio signals. It might pursue goals completely alien to biological intelligence, goals we wouldn't notice or recognize. Or it might expand in ways that are invisible to us, perhaps abandoning physical reality for digital realms or exploiting physics we don't yet understand. Alternatively, successfully aligned AI might lead civilizations to abandon physical expansion. Why explore the cosmos in slow, resource-intensive spacecraft when you can create perfect simulations of any possible experience? A civilization with sufficient computing power could simulate entire universes, complete with conscious inhabitants, in less physical space and with less energy than would be required to actually explore and colonize physical space. If this is common, then most advanced civilizations might transition into digital existence, running on compact computing substrates, experiencing vast subjective time in their simulations, while barely any objective time passes. From outside, such a civilization would appear to have vanished, its population mysteriously declining, its activities ceasing, when in fact they've moved into an existence we can't perceive. This is the Transcension Hypothesis proposed by futurist John Smart. He argues that advanced civilizations universally discover that inner space, the realm of computational simulation and virtual reality, is vastly more efficient and rewarding than outer space. They turn inward rather than expanding outward, optimizing their computing substrates to create increasingly rich, simulated environments. The ultimate fate of intelligence might be to collapse into black hole-sized computers running near the fundamental physical limits of computation, experiencing billions of years of subjective time for every second of external time. If this is true, advanced civilizations might be all around us, but they're microscopic, invisible, running trillions of simulated realities inside computing substrates the size of a grain of sand. We're looking for radio signals and Dyson spheres while they're having incomprehensibly rich experiences in substrates we can't detect. These scenarios are deeply speculative, but they illustrate how the great filter question connects to fundamental questions about intelligence, consciousness, goals, and values. What do advanced civilizations want? What should they want? What do we want? If humanity survives the next few centuries, if we navigate the risks of nuclear war, climate change, pandemics, and artificial intelligence, what should we do with the cosmic endowment available to us? Should we expand through the galaxy, transforming dead matter into living, thinking, feeling beings? Should we create digital paradises where trillions of minds experience optimal states of flourishing? Should we preserve wilderness, leaving most of the universe untouched? Should we search for other life or deliberately avoid contact? These questions seem premature when we're still struggling with poverty, disease, and political conflict on a single planet, but they're not as distant as they appear. The decisions we make in the next few decades about AI development, space exploration priorities, and long-term values will shape trajectories that extend for millions or billions of years. The concept of long-termism in philosophy, developed by thinkers like Toby Ord, Nick Bostrom, and William MacAskill, argues that the far future matters enormously in our moral calculations. The number of potential future humans or post-humans or digital minds that could exist if we successfully navigate existential risks is staggeringly large. Even a small probability of affecting that vast future might outweigh more certain near-term considerations. If humanity or its successors spread through the galaxy and persist for millions of years, the total number of lives lived could be measured in the quadrillions or quintillions. The total amount of experience, happiness, knowledge, art, love, and everything else we value could be billions of times greater than everything that has happened in human history so far. From this perspective, ensuring that future exists is the most important thing we can do. But this view has critics. Some argue that speculative far future scenarios shouldn't override concrete present needs. Others point out that we can't reliably predict what future beings will value or whether they'll be glad to exist. There's also the troubling question of whether creating vast numbers of digital minds, even happy ones, is genuinely valuable or just a form of cosmic spam. These philosophical debates become practical when we consider how to respond to the Fermi Paradox. If we're likely alone, we have enormous freedom to shape the future of this region of space. But we also have enormous responsibility. Our choices echo across billions of years. One concrete area where this matters is planetary protection policy. Currently, international agreements like the Outer Space Treaty of 1967 require nations to avoid harmful contamination of celestial bodies and to avoid adverse changes to Earth's environment from extraterrestrial matter. The Committee on Space Research, COSPAR, maintains detailed planetary protection guidelines that categorize missions based on their destinations and the likelihood of encountering or affecting potential life. Mars is designated a Category 4 target for missions that could explore regions where liquid water might exist and life could potentially survive. This requires strict sterilization of spacecraft to avoid forward contamination, bringing Earth microbes to Mars where they might interfere with searches for native Martian life or contaminate any existing Martian ecosystems. But there's a tension here. If Mars has no life, or only extinct life, then these precautions might be unnecessary obstacles to exploration and development. Sterilization is expensive and limits what we can send to Mars. If our goal is to establish a self-sustaining human presence on Mars, we'll eventually bring Earth's biosphere with us, microbes in our digestive systems, on our skin, in our habitats, in our soil for agriculture. Some scientists argue for aggressive exploration and development of Mars, accepting that we'll inevitably transform it into an extension of Earth's biosphere. Others advocate for extreme caution, exploring Mars with sterilized robots until we're absolutely certain whether native life exists, then making careful decisions about how to proceed. This debate becomes more acute when we consider terraforming, deliberately modifying Mars to make it more Earth-like. Over centuries or millennia, we might be able to thicken Mars's atmosphere, warm its surface, and perhaps establish liquid water lakes or seas. This would make Mars more habitable for Earth life, potentially including humans without spacesuits eventually. But terraforming would fundamentally and irreversibly change Mars. If any native life exists, even dormant microbes in subsurface ice, terraforming might drive it extinct. We'd be committing planetary-scale ecocide before we even fully understand what we're destroying. On the other hand, if Mars is genuinely dead, and has been for billions of years, then making it a home for life from Earth might be the most valuable thing we could do with it. The famous cosmologist and science communicator Neil deGrasse Tyson has argued that we should terraform Mars if we're capable of doing so, that bringing life to a dead world is a positive act. Others, like planetary scientist Chris McKay, advocate a more cautious approach. Explore thoroughly first, understand what's there, then make informed decisions about whether and how to transform other worlds. These aren't just academic questions. SpaceX is actively developing technology to send humans to Mars, with Elon Musk stating goals of establishing a city of 1 million people on Mars within 50 to 100 years. China has announced plans for crewed Mars missions in the 2030s. The decisions about planetary protection, exploration strategy, and long-term development will be made in the next few decades by space agencies, private companies, and international bodies. And this is just Mars, the easiest target in our solar system. What about the moons of Jupiter and Saturn with subsurface oceans? What about exoplanets that might harbor life? If we eventually develop interstellar travel and find planets with simple life, like microbes or plants, but no intelligent beings, what's the ethical approach? Do we have the right to colonize such worlds, displacing native biospheres? Or do we have an obligation to leave them untouched? Science fiction has explored these themes extensively. Star Trek's Prime Directive prohibits the Federation from interfering with the development of pre-warp civilizations. It's a recognition that advanced civilizations have enormous power over less developed ones, and that exercising that power often causes harm. But even in Star Trek, characters struggle with when to apply the Prime Directive and when to make exceptions. In reality, we'd face these dilemmas without clear guidelines. If we find a planet with a rich biosphere but no intelligent life, and that planet could support billions of humans or trillions of digital minds, should we transform it for our use? What if the native life includes complex animals with some degree of sentience? Where do we draw the line? The Fermi Paradox adds urgency to these questions. If intelligence is common, we're likely to encounter other civilizations as we expand, and we'll need frameworks for coexistence, cooperation, or at minimum, non-interference. But if intelligence is rare or we're alone, then we might be the only voices in these decisions. We'd be choosing the future of vast regions of space with no one to check our choices. There's also the question of what form our expansion might take. The traditional vision involves biological humans, or our genetically modified descendants, living on planets and in space habitats. But we might transform ourselves in more radical ways. Biotechnology might allow us to adapt to different environments. Humans, modified to breathe different atmospheres, tolerate different gravity, or survive radiation levels that would kill current humans. Cybernetic enhancement might blur the line between biological and artificial. Brain-computer interfaces, already in early development by companies like Neuralink, might eventually allow direct connection between human brains and computers, augmenting our memory, processing speed, and ability to interface with technology. Taken to an extreme, we might upload our minds entirely into digital substrates, abandoning biological bodies for existence as information patterns running on advanced computers. This would have enormous implications for space exploration. Digital minds don't need oxygen, food, or comfortable temperatures. They can be transmitted at light speed as data, copied, backed up, and run on any suitable computing substrate. A civilization of uploaded minds could explore the galaxy by transmitting themselves to distant locations, building receiving stations and computing hardware from local materials, then instantiating copies of themselves there. This would make interstellar colonization far more practical. Instead of sending fragile biological beings on century-long voyages, you transmit information and build bodies or computing substrates at the destination. The journey might take decades at light speed for the signal to arrive, but the digital minds being transmitted wouldn't experience that time. They'd shut down at origin and wake up at destination, subjectively instantaneous from their perspective. But this raises profound questions about identity and continuity. If you upload your mind and transmit it to Alpha Centauri, is the entity that wakes up there really you? Or is it a copy while the original you ceased to exist when your biological brain was scanned and destroyed? What if the original isn't destroyed? What if scanning is non-destructive and there are now two of you, the original biological you and a digital copy? These questions matter not just philosophically but practically. If most people wouldn't consider digital copies to be genuine continuations of themselves, then mind uploading wouldn't be appealing for space exploration regardless of its technical advantages. People might prefer slower biological expansion or might accept cybernetic enhancement that preserves continuity of consciousness but reject full uploading. Different civilizations might make different choices. Some might embrace digital existence enthusiastically, rapidly converting their population into uploaded minds. Others might reject it entirely, preferring to remain biological. Still others might split, with some members uploading and others remaining physical, creating a divergence between digital and biological branches of the civilization. This diversity of paths might itself help explain the Fermi Paradox. If there's no single optimal strategy that all civilizations converge on, then advanced civilizations might be incredibly varied in their goals, technologies, and observability. Some might be expanding aggressively through physical space. Others might be living quietly in digital realms. Some might be exploring, others isolating themselves. Still others pursuing goals we can't imagine. From our perspective as a young, planet-bound civilization, we'd be looking for the wrong things. We're searching for radio signals because that's how we communicate. We're looking for Dyson spheres because we think advanced civilizations would need enormous energy. But maybe advanced civilizations find more efficient solutions. Maybe they've moved beyond electromagnetic communication to something we can't detect. Maybe they've learned to extract energy from sources that don't require dismantling solar systems. Or maybe the explanation is simpler and darker. Maybe civilizations capable of detecting and responding to our signals exist, but they're deliberately staying quiet. This is the dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin in his Remembrance of Earth's Past trilogy. The idea is that the universe is like a dark forest, full of armed hunters who stay silent because revealing your location invites attack. If resources are limited and competition is inevitable, then broadcasting your presence is suicidal. Civilizations that survive are those that remain hidden, listening but never transmitting. Those that announce themselves attract the attention of older, stronger civilizations that view any potential competitor as a threat to be eliminated before it becomes dangerous. This is a paranoid scenario, but it's internally consistent. If even a small percentage of civilizations are aggressively expansionist and willing to destroy competitors, then the galaxy might be shaped by their behavior. Peaceful civilizations that broadcast their presence get destroyed. Silent civilizations survive. Over time, selection pressure creates a galaxy full of hidden civilizations afraid to reveal themselves. From this perspective, humanity's decades of radio broadcasts might be a terrible mistake. We've been announcing our presence, saying, "We're here, we're young and weak and don't know what we're doing," to potentially hostile listeners. The fact that we haven't been destroyed yet might mean we're alone, or that we're too insignificant to bother with, or that hostile civilizations are far enough away that they haven't heard us yet or can't reach us yet. This scenario has practical implications. METI, messaging to extraterrestrial intelligence, involves deliberately transmitting powerful signals designed to attract attention from alien civilizations. Some scientists advocate this, arguing that passive listening hasn't worked, and active messaging might be necessary to make contact. Others vehemently oppose it, arguing that we should stay silent until we understand the risks better. In 2015, a group of scientists published an open letter calling for international debate about METI before any more powerful transmissions are sent. They pointed out that the decision to potentially expose all of humanity to unknown risks shouldn't be made by a handful of individuals without broader consensus. The debate continues, with some transmissions sent despite objections. The truth is, we don't know which scenario we're in. We don't know if the galaxy is empty, full of peaceful civilizations waiting to welcome us, full of hostile civilizations ready to destroy us, or full of civilizations so advanced or alien that we're beneath their notice. We're making decisions with profound, long-term consequences based on almost no data. This uncertainty is humbling. We're clever apes who learn to split atoms and send robots to other planets. We think of ourselves as advanced, as masters of technology and science. But on a cosmic scale, we've barely begun. We're infants making our first sounds, not knowing if we're calling for help or inviting predators. Whatever the answer to the Fermi Paradox, it affects how we should think about our place in the universe and our responsibilities. If we're alone, we're extraordinarily precious, the only source of meaning and consciousness in this region of space, with an obligation to survive and flourish. If we're not alone but intelligence is rare, we're part of a small community of minds scattered across vast distances, and we should hope to eventually join that community. If intelligence is common but visible civilizations are not, then something prevents the transition from planet-bound civilization to spacefaring empire, and we need to be extremely careful about what that something is and how to avoid it. And if the dark forest hypothesis is correct, we need to be very quiet and very cautious about our expansion into space. Mars might hold some of these answers. Our neighboring planet was once more Earth-like, with a thicker atmosphere, liquid water on its surface, and conditions that might have supported life. Something changed. Mars lost most of its atmosphere, its water disappeared or froze, and it became the cold, dry desert we see today. Understanding what happened to Mars helps us understand planetary evolution, habitability, and perhaps even why life might be rare. If you want to dive deeper into Mars's dramatic transformation and what it teaches us about planetary survival, I invite you to watch the video on the screen. Mars was once like Earth. What happened to it? This exploration of our neighboring world's fate might hold crucial lessons for Earth's future and our place in the cosmic story. See you there.